Hi, everyone. Question, our exam will be in person or online? It should be in person already. Well, the class should be in person too. So as soon as possible. So it looks like it's scheduled for February 2nd. Yeah. Yeah, the thing is with online exams, many things are difficult. So there's just no way for us to prevent you from using any tool whatsoever. So it's very easy to ask easy questions. It's difficult to ask easy questions because you can just look at any textbook or note, or so in a way we have to ask more involved questions. Also, there's always the issue of you have to do it by yourself, but we cannot check that because it's too hard to proctor. So all of these things make it much easier to them in person. Plus, for you, it's very stressful to have to scan everything once it's done and upload that to Moodle and make sure it's in the right format and it's graded appropriately. So yeah, it makes everything complicated. All right. So I've just realized that the link I posted on the class website for the class Moodle for the quiz was wrong. So the link in the class notes was okay. But yeah, the link in the class website was wrong. Anyways, we can still do it together and see what happens. So sorry about that. By the way, you can hear me properly, just to be sure. And to be sure I can hear you properly.
I can hear you.
Yeah, good. First assignment. So I should post the first assignment Thursday, sorry, Tuesdays now. And it will be due on February 3rd. Yeah. So you will have 2 weeks to do it. Yeah, and I've also posted the first TA session. So that's extra exercises and all the stuff we've seen so far. So yeah, after today, you should be good to do all of it. I thought the first TA session was on Friday, but I'm not too sure. So I'm in contact with the administration about this. So I'll post you as soon as I have other news. Yeah. I thought it's week 3rd, and since the classes started on a Thursday, then it means that the third week should start Thursday, Friday. Yeah. Okay. So about is there anything else? No, I think we're good. Okay. So if you don't mind, let's start. Why don't we start with the quiz actually? So that's just to warm up a bit. Also, yeah, a bunch of you did it. Perfect. All right, so let me share with you my screen. Okay, given the set S1, S2, S3, and S4, which statements are true? S1 equals S3. Yes, so 80% of you got it right. Why? Because it's the same set, just the order of the elements are reversed. But as we've said, the order of elements doesn't matter. This was wrong because the caret isn't in the set 1. Set 3 is included in the reals. Well, no, because an elephant is not a number. So if you have doubt, maybe philosophically anything can be anything, but yeah, an elephant isn't a number. S4 is included in S2. So S4 is rabbit, monkey, and S2 has no rabbit inside it. So yeah, it's not included. So it's not a subset. S4 is a subset of S1. Yes, so rabbit, monkey, elephant, so that's good. S1 is a subset of S3. So this is, as I've said, I'm going to assume in this class that this symbol means either a strict subset in the sense that S1 has fewer elements than S3, or maybe the same set as well. So since we have established that it is the same set, so this is valid too. So yeah, all of you got it. Empty set is a subset of S4. Well, yes, the empty set is a subset of any set, whatever the set. So that's yeah. It's like if you have a bag and it's empty. So and then you have another bag with stuff in it, and can you take out the empty can you take out nothing from a bag that has something in it? Well, yes, you just put your hand in it and take your hand out with nothing in it. So that's how you get to include the nothing set inside any set. So yes, of course, stop me if you have any questions about this. Given the sets rabbit M1, snake M1, and 1 rabbit M, what elements are contained in S1 intersection S2 union S3? So this is quite easy. All you have to do is really to follow the order of operations. So S2 union S3 gives us snake M1 rabbit, and then intersection S1. So the snake isn't in it, but M and 1 and rabbit are in it. Yeah, so all of you got it. Nice. Given the sets S1, S2, S3, what elements are contained in S1 union S2 intersection S3? So it's basically the same thing there. So yeah, I said that yeah, okay, this is better. So S2 inter S3, so I get M and 1, and this union S1, so M1 rabbit. Yeah. So the snake is not in it. Given any set S and a universal set U, what statements are true? All right, so these were maybe a bit more challenging, but still. So S union intersection equal S union empty set equals beer? No, because, so just to be clear, if I just give you beer here, I haven't even said that beer is a set. So it has to be a set first of all. So so yeah, it could be just an element of a set or anything. So it's, since I haven't given any definition, so that's not true. S inter empty set is the empty set. Yes, which element is common with the empty set and any other set? That's just an empty set. So there's nothing inside it. I have questions there. Okay, no. Perfect. S intersection S, S union S is the universal set. Oh, that's maybe I shouldn't have chosen U, because this really looks like it. Yeah, I should have changed the symbol. But anyway, so S union S is S, so it's not the universal set. S intersection S is S again, so it's S with union with itself, or intersection with itself is just always itself. So it's always S. So this is wrong, this is wrong. And S intersection U is S, yes, because S is some set and U is all of the other things I could consider. So what are the common elements? Well, it's whatever it's inside S and not outside of S. So yes, so this is true. Yes, it's just just to start our brains thinking about things, so nothing too complicated. Maybe it's going to be a bit more complicated in the exercises or the quizzes. But yeah, I think most of you got it mostly right. So questions about this before I move on? No? All right. Oops. Okay, so today we finish chapter 2. Yeah, I think we should be able to do it. So we finished with linear equations and inequalities. And now we are going to introduce to other things like quadratics and stuff. All right. So quadratic relations. So let's have a simple one. So imagine that my relation is x equals y squared. So why is it quadratic? Because I have this square here. And so how should I represent this? So this is x equals y squared, but I could also take the square root. What would I get? I would get that square root of x is equal to, yeah, so that would give me, yeah, no, that's plus or minus, sorry, equals to the square root to y. Why? Because here y can take two values for it to be equal to x, because it can take positive and negative values. So this is, I should include this. If you're not sure, just take your original equation and graph it, and you can know whether you forgot any values inside it or not. All right, so let's represent. So how many points would I need to represent this? Or no, not this function, this relation, sorry. Yeah, that's better. So three at the minimum. Yeah, 3 is fine. 4 could be even better, just to make sure that the. So let's use 3 points to draw it. So let's take simple ones. So for instance, let's have, if, so we'll start with this. So x equals 0, y equals what? 0, that's easy. And then x equals, say, -1, y equals what? Are you sure? That was a trick question. Yes, so I challenge anyone to take any number, square it, and get -1. Or yeah, rather, can somebody tell me which number I would have to use? DNE, what's DNE? Does not exist, yeah. But one could exist. So I could take I equals square root of -1. So if I take this square, then I get -1. So, but we don't care about these. And if I don't say what X and Y are part of, then you're free to assume that they're part of the reals, as I said. So otherwise, I would just spend the whole class saying, by the way, X is real, blah, blah, blah. So no time for that. So that's a trick question. But if X equals 1, Y can equals what? Can equal what? Yes. And is that it? Could I have something else too? Yeah, good. Or -1. So 3 points. Going to have 0, 0. 1, 1, and 1 -1. So I just represent this to show this is the set of points I'm going to use. Don't have to always write all your answers in terms of sets. Yeah. Okay, so let's do that. So I assure you that at some point in this class, you will have to draw stuff. So better get used to how it's done. All right. So let's put some numbers on it. So 1 -1. Here, 1. And I have 1, 1, 1 -1, and 0, 0. So that's a good indication of the shape of my functions. It should look like this. No, not good. How should I do that? Let's do it by, okay, let's start again. So we're not, it's not an art school. So maybe there's an art school in Concordia, but it's not an art class. So this will be fine. If you do something like this, that's I'm more than happy. All right. And you can indicate what points are what, just to be sure. But since we have coordinates, it really looks like we know what we're doing, but still. So here we have 1, 1, 0, 0, and 1 -1. So just in case somebody has doubts, so yeah, I should have maybe said that this is the x-axis, this is the y-axis. So we should usually put the x on the horizontal and y on the vertical axis. And we usually represent the first coordinate as the x point and the second coordinate the y point. Yeah, thank you. So that was now I don't have any punchline. So yes, the punchline is this isn't a function. So thank you. As we haven't described what is or isn't a function. So I can tell you already. So a function is a relation for which each set of points on the x values is associated with at most one point on the y values. And here that's not the case. To see whether it's the case or not, you just have to look at one value, for instance, and lo and behold, there's one value and two values associated with it. So you know it's not a function. So thank you. Very good, astute observation. Or some, but in that case, are admissible. X values. To y values. Then, so this is exactly where we were going next. So let me just save this. Yeah, maybe we don't need this. Just all right. Okay, so since we were talking about functions, so let's go ahead and talk about functions. So if you don't like this topic, then blame it on your friend there who started talking about it. So now that's the new topic. So a function is a relation such that each x corresponds for each x corresponds a unique y value. And as was pointed out astutely, so the relation was not a function. So how do we write this? We have many ways of writing it. So, yeah. So we can write something like y equals f of x. That's mostly how I learn how to write it. So that's the way I write it usually. Or sometimes you may see something like function f, which is defined as the relation between x and y, like this. So this is what you would say is a mapping. So f is a sort of machine which takes values x and maps them onto values y. All right. So for example, so y equals square root of x. So in that case, it's only the positive values. So that's good. Another example is, of course, y equals x squared. So just a bit more vocabulary. So the argument. Of course, these are functions of single variables. We're going to see functions of more variable. So the argument here is x. The value of the function is y. You could see, or sometimes you may read the map or the image. But yeah, value is fine. Just to help you if you hear other things. And now, specific to function, the domain is the admissible values for x. So values for x for which the function can be computed. And the range is all possible values of f of x given f and the domain. So by the way, somebody has heard of the expression codomain? No, not necessarily. Because if you have y equals x squared, so that's not one-to-one because for certain values of x may have two values of certain values of y may have two values of x. All right, so since we are introducing this, so one-to-one means yeah, codomain, good. For each value of x corresponds a unique value of y, and for each value of y corresponds a unique value of x. So of course, this is a function but is not one-to-one. Sometimes you may call this a bijection. But that's so though that this is like I'm going to put this in brackets because this is going like it's that's might be useful someday, but it's not something that's too useful for this class. Yeah, so other expression, I'm also going to put this in brackets. So not confuse domain range with codomain, which may include more values. So I've read the definition of codomain, and I think this is more of a matter of specifying a set of values that you accept for a specific problem, whether or not the values, the function that you are evaluating can or cannot have it. So for instance, if my function is y equals square root of x, then square root of x is just going to be in the positive values. Yeah, and x is because x can by itself just be in the positive values if it's real. So then y couldn't be negative. But if I could say that the codomain I am allowing is the whole real numbers for y2. So, but yeah, that's nitpicking. That's if we continue for a more advanced math class, but this is not. Yeah, so codomain. And range. But really, you shouldn't waste sleep on this. If I put it in bracket, that's just for your own instruction, your own free time. Okay. So questions. If I have the function y equals because so if you draw it, this is just going to be this, but rotated this way. And there you can have for one value of x, say 1, you're going to have 1 and minus 1. Yes, exactly. Okay, y equals x squared. Yes. Yeah, bijective is like 1-to-1. Or not? I'm having doubts. I didn't expect to answer all these things. So I don't want to mislead you. So bijection, yeah. Okay. Here we go. So Wikipedia. Bijection, bijective function, or one-to-one correspondence, or invertible function. All of these are the same thing. Is a function between the elements of two sets where each element of one set is paired with exactly one element of the other set. And each element of the other set is paired with exactly one element of the first set. Okay. Oh, I'm breathing better. So yeah. I'm not using the word bijection and one-to-one in everyday conversations usually, so I've just had to check to be sure. Okay. All right. No, we're all learning there. So, so question for you. What is the largest possible domain and range? Yeah, infinity. Can you be a bit more precise? Yeah. So Okay, let's start with X. X can take what values can X take? Yes, good. So Timothy 1 and Y. Yes, so this is good. Yes, okay, good. I have seen all the right answers. So what we would say is that this function is such that xy is element of R, and what you would write is R plus. All right. So that's just the positive values of, or you would say to that. So if we you would say you could write also minus infinity smaller than x smaller than infinity, or x element of minus infinity plus infinity. So this is to represent a range of numbers. And okay, for example, this would be an acceptable way of representing the elements of X. This also, given that we, as I said, if we don't say anything, then these are real numbers. And by the way, so there's a different ways of representing ranges of value. So yes, okay, perfect. So the way to represent so we would have so if I have this is A and this is B, so just A, B are just the limits. So if I'm saying that X is strictly greater than A and strictly smaller than B, so I'm representing this way. So I say that X is strictly greater than A and strictly smaller than B. And I'm going to write this means X, and then I'm going to use square brackets for this. X is, I would say it's weakly or is greater or equal. A and smaller or than B. Yeah. All right. And by the way, you cannot say something like this. Doesn't work because yeah, So I don't know all the specific details about this, but there's no variable, no value may equal infinity. That's just the way I see infinity myself is yes. So it's just something that is arbitrarily large as you want it to be. So it's, if you say no, but x equals is very big, it's 10,000. No, well, my limit of my range is even greater than that. Yes, I'm going to put x's in front just to warn you. This doesn't work. All right. Yeah, so it's unbounded. All right. Okay, another example. So y equals square root of x. What is the largest possible domain and range? Yeah. For 3 numbers. So no. Yeah, 0 to infinity for x. And what does that mean for y? Yes. So here what we have to start with is see that this cannot be evaluated for negative x, for negative values of x. So it, but it has a value for any positive value. So we know that x is in the positive reals, and we represent it this way. And since x is in a positive real, then this has a constraint on the range. It means that y will not be negative. In another world, it could have been, but here, since x is constrained to the positive values, then I'm going to have y as well. Of course, if this was the case, then that would be the opposite. I would have r minus there. But I don't have a minus in front. All right, so this is the sort of questions you may want to ask yourselves. So if you think a bit about it, I think it's doable. I'm not going to ask you very tricky questions. Yeah, hopefully, from my point of view, at least. All right. So just to say the comment what I did. So x may not be negative because the square root operator, and y is also well, so have only positive values as a consequence. All right. Okay. So let's continue with popular functions in economics. So polynomial functions are some. So you could have the simplest one is y equals 4. So this is called constant. And it's not even really a function because in our common way of understanding things, so if we say that something is a function of something else, then it has to be somehow affected by it. So here you could say it's 4 plus 0x. So whatever x, the value of x, then the value of y does not change, it's constant. But yeah, we still say it's a constant. It's a kind of function, although it's not a very useful one. One that is very, very, very widely used is, I'm going to write it this way, mx plus b or ax plus b, or yeah. So it's first order. Also known as near, or in French, sometimes you may see affine. Is that there? Does you need 2 F's or 1 F? I'm not sure. Yeah, 1 F. Or 2 F's. Oh, no, 2 F's, sorry. I think you can still see that in English, but so anyways, that's a very convenient one. And then another one, quadratic. So x2 plus 2x plus 4. So you would say it's second order. Also known as quadratic. Then let's have another one. So y equals x3 minus 4 x2 plus 2x plus 4. So that's third order cubic. And it goes on and on and on. And nth order, you would represent it this way. Y equals, so now we have to start from the opposite. So a really general way of representing it, it would be a0, x to the 0, which is 1. So that's your constant term there, plus a1, x1, plus a2, x3, plus n, xn. So that's x2, a3, x3. So yeah, it's not too thrilling, it's just definitions, but yeah, we need a common vocabulary to talk about things. So that would be an nth order. Yeah, so polynomial functions is functions with numbers, natural as exponent. Yeah, sure. So what you see is the order is determined by the largest exponent of x. So yes, here you could have something like a0, a1, a2, a3, up to an minus 1 could be r0, and it would still be a nth order polynomial, because what matters is the last term here. The last non-zero, the coefficient, yeah, of the largest, yeah, so the largest, it's the largest exponent of x for which there is a non-zero coefficient. Okay, that's the way you should say it. All right, so those are very, very useful, and we're going to use them quite a bunch. Other functions, rationals. So that would be y equals 1 plus x squared divided by 1 plus x. So they are ratios of two polynomials all right, so no confusion. I could give another example. So y equals 4x4 divided by 1 plus x. I don't think that simplifies, but no, it doesn't. Now, other, so any non-natural exponent, such as, for instance, y equals square root of x, which is, of course, equal to x to the 1/2. Or you could have y equals x to the minus 1.5. So that would, yeah, that would also qualify as rational in a way. But no, not really, because it's yeah, no, it's not rational. It's more general than that. All right, so, and then a big other group, so non-algebraic. Yeah, nice suggestion. Like exponential. And here I'm just going to flip the exponent and the variable. Yeah, great. So y equals e to the x. And this we also sometimes, if it's the natural logarithm, then we write it in x. Sorry, x of x. And then you could also have y it's 2 to the x. So this one can be quite useful in some instances. Yeah, good suggestion, logarithmic. Y equals log of x, so that's a natural logarithm. Or yeah, in general, you could have y equals of x. Yeah, so those are all the functions that we could find. But you could all encounter them in economics. They're all popular. And then, of course, functions. Trigonometric functions. Yeah, I would say they're pretty rare. So if you have dynamic models, then they could show up. For instance, I've been teaching a class, a macro class on growth. And so one part was a solo model, which is quite, yeah, it's quite harmless, but there was one that was a bit more complicated. It's the Easter Island model. And what happens in the Easter Island model is like a predator-prey model. So when you have, so imagine that the predators are high, then they eat all the prey and the prey go down, and then the predators starve, so they go down. And then since predators are rare, then the prey go up again. So you see that you have these cycles that show up. So this is something that you observe in nature between lynx and all of this. But then, so there was a very nice paper by Scott Taylor and Brander. Yeah, what's his first name? Yeah, Brander and Taylor. Anyways, about the dynamic of the Easter Island. So somebody knows Easter Island? So it's an island in the Pacific that's completely barren. That's close to Chile. It's quite cold there. And so yeah, nowadays there is a small population, but yeah, there are big statues that you may have seen. And one of the paper to explain it was essentially saying what happened is when the island was colonized, there was a forest. And then so the people who arrived on the island started using the forest a lot, but it depleted the forest completely. And then they almost disappeared, the population crashed. And then the forest, well, in that case, didn't really recover, but yeah, in the model, you could have these sorts of cycles. But yeah, so that's pretty advanced stuff. So nothing you should worry too much about. But yeah, in dynamic models, in macro, in finance, you may observe cycles. Yeah, every time you have something that's turning around, then sines and cosines can happen. Yeah, cyclical. Okay, where was I? Logarithmic, yeah, functions of more than one variables, of course. So let's start with two variables. That's complicated enough. So you would write it this way. So let's see. Goes f of x and y. Or you would also write it here. F is a function that takes in as argument a pair of numbers x and y, and spits out one value of z. So how would you represent this? So it takes a surface. in the yeah, exactly. So you start with a value on the XY plane, and you map this onto an other axis. Yeah. In the X, Y, Z space. Oops. So do you know a famous function of two variables that you may have seen before in economics? Don't remember. First person is Cobb. Yes, Cobb Douglas. Yeah, very convenient one because it's just so easy to work with. So example in microcon. For utility or production function. So x1 x2 equals, here I could just give one, so x1 to the 0.5, x2 to the 0.5. Yeah, so that's quite an easy one. Yeah, so in macroeconomics, that would give you constant returns to scale, meaning if you double the input of input 1 and double the input of input 2, then it means that oh yeah, so that's utility, of course. But if it was a production function, then it would double the production. All right, so I can show you what this looks like. So I've done a small graph in Julia of this function. So it looks like a mountain. By the way, have you ever looked at this in 3D? The thing is, I only saw Cobb Douglas when I started my master's degree, so you're quite early on in your economist career, but yeah, I switched late, and people were talking about it, but I was doing computation with it, but still I had never visualized what it looked like. So if you look at it, it really looks like a mountain that's always increasing. So you have, so for instance, X in here and Y here and Z here, and you see that the larger the value of X and the larger value of Y, then this goes up forever. Yeah, exactly. So this is a super good point. So by the way, very good resource to plot any function. Google. So I invite you to just write something like y equals x to the 0.5 plus y to the 0.5, and I think that should work. You can try it on your own. Oh, no, it doesn't. Oh, no, no, I've, why? Yeah, Z, so that's better. And yeah, it gives you something in 3D, and of course, if it's going to work too in 2D, so you can graph any sort of functions. So I invite you to use this as much as you want for assignments, for instance. That's very useful when you're trying to find the zeros of a function or anything. I'm still going to require you to justify your answers. So just saying I Googled it and here's the answer is not a valid justification. But yeah, it's very useful. So it's 2022, so we have to use all the tools at our disposal. But of course, if the exam is in person, then sorry, you cannot bring your laptop to the exam. You have to do it by hand. So you use it as much as possible to help your understanding, but be sure that you're able to still figure out what's going on, even if you're not using it. All right. So that's one. By the way, I don't know if you know Julia, but just in case, I'm going to write the code for that. So Julia code. So you write using plots, and then you write this function there, and so you just define your function, u of y, x and y equals x to the 0.5 times y to the 0.5. What did I write? A plus here? Oh, yeah, this is better. All right. Yeah, so you just define your function there, and then you can just write surface, and you can just tell it, I want a range from 0 to 5, 0 to 5, with the increment of 0.1, and I want to plot the value of the function. And so just in case you want to reproduce this and you don't know how I did it. You can also ask me and I can tell you. Also, there's a nice one you can use is contour instead. Contour is going to give you contours, so I'm going to show you with contours what you get. So you get this. So what is this? These are sort of yeah. These are the value of x and y for which the value of z is constant. So it's like if you have a topographical map of a terrain, then you look at the altitude. So this is higher, this is lower. So of course, this part here is like this part here, right? And so by the way, question for you. So if we have, if it's a utility function, what are called the contour lines? Yes, of course. In the exam, I'm going to ask you to graph a three-dimensional curve surface like this. Of course, I'm going to ask you to do that. It's just so useful. That's the best thing you. Yes, good. So by the way, I'm joking. So no, I'm not going to ask you to draw a three-dimensional shape. I can't. I have no clue. I would do. I could try and do something maybe if I had time, but yeah, it's just that's not the point. So answer. So they are indifference curve. So yes, exactly, yes. So the question is, contour lines is a function of two variables, yes. It's a representation of this function there. But also what we are going to see later is that, so what you could say is, I'm going to select, for instance, that, so imagine though this is the value 2 there, so this is z equals to 2. So what I could do is say, oh, I'm going to use my razor blade and cut this thing right at this level, and look at what is the intersection of this plane at z equal 2 and this 3D surface. And what I would get, of course, is this exact contour line there. And what is this contour line? Well, now this becomes a function of one variable, so a function between x here and y here. And this is something that we see at the end of the class, but it's called the implicit function theorem. So what it says is, if you have a complex function of many variables, then you can always pick a point somewhere and then make two variables vary with each other, and it's going to help you to trace some function between one of the variables and the second one of the variables, as long as the derivatives exist in this this sector. So that's way advanced, but just to tell you what's going on. Okay, lastly, just before we leave, two small things. So function of more variables. So example, linear function. So if I have something like f of x1, x2, xn, which would be equal to a0 plus a1 x1 plus a2 plus an xn. So that's linear, because the only highest coefficient for every variable is 1. So that's a linear function, but I have many functions in my function. And this is, we're going to have a whole lot of fun with linear functions of many variables and linear systems and all these things. So just get ready. And just before leaving, I'm going to give you the that work. So a quiz and function. So here on the quiz, there are things that I didn't explicitly show in the class, but if you remember a bit high school, or you could find out, or if you just dig a bit deeper, you can find it. Oh, this I think should be there. Does that work? Yeah, I'm going to, maybe I'll try to generate a better link for it. So okay, I think this should work. So I'm going to post it in here. So that's a fun small quiz and function. Shouldn't be too complicated. All right, so questions before we go our separate ways? No, all good? Okay, so next time I'll see what's up with TAs, TA sessions, and I'll keep you posted. And yeah, so I see you on Thursday. Have a good day, everybody.